So let's do a couple of examples using radar. So first example problem. Let's imagine that we've got a street here, divided road, and we've got two cars here driving along here, and we've got a cop over here with radar. So we have a police radar and is bouncing radar off these cars. Now, one car is going a little bit different speed than the other, and so the police officer wants to point at the faster car. Okay, now here's the thing. The radar is going to spread out and going to reflect off of both. So the question is, even if he aims at one car, he's going to get a reflection off of the other if it spreads by too much. And so the question that we have is, what distance here, if the two cars, let's assume that the two cars are 3.5 meters away from each other, and let's say that the radar has a frequency of about 25 gigahertz. So I want to know at what distance can the police officer actually resolve one car versus the other car if this is the separation and if that is the frequency. Okay, so we need to know, first of all, the size of the radar emitter. So let's say that the radar emitter has an aperture of 7.5 centimeters. Okay, so this is a resolution problem. And if we assume, making life easy, assume this is a circular aperture, then we know that 1.22 lambda over the aperture, small angle approximation, it's going to be y over x. Okay, and so we know everything in here just about, so we can just solve for x. Okay, so x is going to be equal to 1.22. No, x is going to be equal to a times y divided by 1.22 lambda. Okay. Now, the problem is we need to know lambda in order to use that. Well, we can find lambda from the frequency. We know that speed equals lambda f, so lambda is going to be c over, lambda is going to be c over f. Okay, radar is a form of light. This is microwave, so 3 times 10 to the 8th meters per second divided by 25 giga is 10 to the 9 hertz. Okay, and so the lambda, the wavelength turns out to be 0.012 meters, or about 1.2 centimeters. And so now x is going to be equal to a y over 1.22 lambda. So a, the separation of the vehicles, 3.5 meters. The aperture was 0.075 meters, 1.22, and the lambda was 0.012 meters. Okay, and so x comes out to be about 18 meters. So for using that particular radar frequency, then you have to be within 18 meters in order to resolve two vehicles that are about 3.5 meters apart, side by side. Now, this is one reason that modern police radar is actually moving away from those frequencies to higher frequencies. The higher the frequency, the smaller the wavelength, and so the bigger the distance you can actually go. In Texas, state troopers actually have moved away from radar altogether, and they use lasers. Lasers have, it's light, and it's usually an infrared laser, so it's infrared light, so that's still going to be vastly smaller wavelengths than this. So that would be wavelengths that are considerably smaller, so maybe 100 times smaller. So that means that this would be 100 times bigger. or in other words, about 1.8 kilometers. And so that's why the state troopers have switched to using lasers instead of radar to pick out an individual vehicle in traffic. Other police radars, which are lower frequencies, they're good at picking out one car or a big vehicle, but have a worse time at the smaller vehicles. So that's one example of radars. Let's do another. Let's say we have two fighter jets, and so we got two fighter jets on attack somewhere, okay, and so they are flying some distance y away from each other, and there's a radar station over here that is using military radar, which is 65 gigahertz, much higher frequencies, and these two aircraft are a distance of 12.1 kilometers away. So the question is, how close together do they have to be flying so that on the radar they look as one blip on the radar screen and you do not see two separate aircraft? So in other words, how close together do they have to be flying so that they're hidden so that it looks like just one object? So again, make this easy. We're going to assume this is a circular aperture. And so the resolution is 1.22 lambda over A, and then small angle approximation, that's going to be the y over x. Okay, so this is my x right here. And so 65 gigahertz, we do the exact same thing that we did before. We're going to say that lambda is c over f. So that'll be 3 times 10 to the 8th meters per second divided by 65 times 10 to the 9 hertz. So the wavelength is going to be 4.62 times 10 to the minus 3 meters, or in other words, millimeter wavelengths. And so now we're trying to find y. So y is going to be 1.22 lambda x over A. And so that's going to be 1.22 times lambda, which is 4.62 times 10 to the minus 3 meters. Oh, I forgot to tell you the size of the radar dish. We need that. So let's assume that A is 5.5 meters. Okay, so again, military, big dish there. Okay, and so and then so this would be like a shipboard thing, not a small station. So x 12, so that's going to be 1.21 times 10 to the 4 meters, and then we divide by A, which is 5.5 meters, and so the answer is that they have to be flying 12.4 meters away from each other, so very, very close together, practically wingtip to wingtip, in order not to be visible. Now, this is saying, let's think about it. If it was farther away, then that means this number would be bigger, and so they could be farther apart. If instead of flying towards like a cruiser or destroyer that has a very large radar array, if they were flying towards a smaller base that had a much smaller radar dish, say a radar dish that's only 2 or 3 meters across, that would make this number smaller, which would make that number bigger. So that means that the bigger the radar dish, then the closer together they have to fly in order to hide in each other's radar signature. And it also means that the other thing is the radar frequency. Again, the military frequencies typically are far higher than civilian frequencies, and that makes the wavelength much smaller. That gives greater resolution to be able to pick out individual targets. Many years ago, military radar, for example, World War II, was nowhere near this high a frequency. It was actually in the order of hundreds of megahertz, not gigahertz. So that meant that hundreds of megahertz, that's almost like 1,000 times lower frequency, which means about 1,000 times bigger wavelength. So that means that you would have things that would be a kilometer apart and still look like one blip on the radar if you were at that distance right there. And so that's the kind of issues they had at that time. And of course, you know, militarily, you're trying to not have those kind of problems. And so that's why the push to very high frequencies and very large dishes right there.